this is exponentially small. By Jordan's lemma, you can prove that this part is small, a zero contribution. So I can add to it and meet up with the SIP. SIP goes something like this, right? So now this SIP, together with this additional contour that looks like this, form a closed path. Okay? So you have to see this in your mind because the picture is rather complicated. Because it involves part of the complex plane in the lower Riemann sheet, part of the complex plane in the upper Riemann sheet. But then there's no singularity between these two parts. Because I deliberately removed the pole from this problem to make it simple. So as lambda gets bigger, or as the observation point gets larger, what are the critical points? The critical point will be this one, the setup point there, as we have seen before in the asymptotic expansion, plus this point. Because as the lambda gets bigger, integration along this path is along a simplest descent path. Things become exponentially small very quickly along this path. But most of the contribution for that integral will come from there. Okay, so what we conclude, very similar to this conclusion over here, that integration along SIP is equal to integration along P1 plus integration along, let me call this S2. Okay, S2. Integration along P1 would have the contribution from the setup point as a critical point. Integration along S2 will have the branch point as a critical point. So usually the branch points, the singularities, the setup points are the critical points. There's no pole in this thing. When you go through the analysis, then what you see is that this setup point contribution is exactly like the term we have found using the stationary phase point method a lot quickly. Okay. But then what about the branch point contribution? What kind of weight does it give rise to? Well, one of the things you can do is that the critical points means that the phase of the wave would mainly be like the phase of this point in the complex plane. So if I look at the phase of the wave, this is how the phase point looks like. Okay. At this setup point, this becomes either the chi rho. K rho becomes K1 sine theta I rho plus K1z becomes K1 cosine theta I z plus 2d1. This is how the phase looks like at the setup point, at this point over here. But we can rewrite this as something else, right? Rho is just Ri. Is it sine theta I? I had the picture over there. I think so. Okay. Rho is just Ri sine theta I. And then Z plus 2d1 is Ri cosine theta I. Right? Those are the geometry I had. I had a picture. If you can recall this picture I had that has been erased. Those are the two phases that I have. And then you plug that in there, this would be e to the I k1 Ri sine squared theta I plus cosine squared theta I, which is e to the I k Ri. So this produces a spherical wave, as we have found before using the method of stationary phase. Okay? That produces a spherical wave. And then the proper constructive and destructive interference will give you the denominator, the proper amplitude. What about this other point? Since most of the integration will come from k rho equals to what? What should I set k rho equal to if most of the contribution is going to come from that point over there? What should I set k rho equal to? K rho. What is the value of k rho over here? So if I integrate along the complex plane, k rho is going to come from mainly this point over here. What is the value of k rho there? What? K2, very good. So I set this to look for the wave that is associated with this point. Set k rho equal to K2. So it would be a wave that looks something like this. K1 squared minus K2 squared. C plus 2D1. But usually K2 is larger than K1. So this actually is a wave that looks something like this. Minus K2 squared minus K1 squared C plus 2D1. What kind of wave is this? Yes? A surface wave, right. It decays in the z direction. It propagates in the rho direction using the wave number of region 2. Okay, what this means is that it's a wave that looks something like this. I have region K1, K2, and I have a direct wave that you can calculate because I just ignored the direction. I have the setup point contribution that corresponds to this, which is the same as the stationary phase point contribution. But then I have a branch point contribution that contributes to this wave. How does this wave look like? This wave is a wave that propagates radially with a wave number of region 2. It propagates like that. But then it's evanescent in the z direction. So it's actually excited by an evanescent wave. And then it is a wave that decays like that. What kind of wave is it? It propagates with a phase velocity of region 2 in the rho direction. So it's a wave that goes into medium 2 and comes back to medium 1 as an evanescent wave. Okay? So you can think of this wave as being something that if you have a source very close to the ground, that it will actually have K2 is larger than K1. So it produces a spherical wave in region 2. It has a shorter wavelength. And then this other wave actually has a spherical wave in region 1 that has a longer wavelength. So this wave would actually propagate like this with a shorter wavelength. But then as it propagates, because it propagates with a slower phase velocity than region 1, it produces an evanescent wave. So it's actually part of the spherical wave that propagates in region 2 that is observed in region 1. That's what the K2 branch point is. It has this wave number K2 rho. Okay, but evanescent in region 1. Okay? I think we'll stop here since people are waiting for us to leave this classroom. Are there any questions regarding this critical point analysis? So I don't want you to go through the mathematical detail, but just learn how to identify critical points on a complex plane and try from these critical points elucidate the physics, what they mean physically. One is a spherical wave, the other one is a surface wave. And this is also called a lateral surface wave. Okay, we'll talk more about this and we can reconvene again next Tuesday at 9 a.m. Okay?